Right now, your phone only knows exactly where you are because two clocks completely disagree about what time it is. A GPS satellite in orbit ticks exactly 38 microseconds faster every single day than a clock down here on Earth. If our devices didn't constantly correct for that drift, your map position would be off by kilometers within a single week. The classical explanation for this drift is relativity. Mass curves spacetime, meaning clocks situated deeper in a gravity well take slower. The math for this works perfectly, but there is a limitation. The math describes exactly what happens to the tick rate without providing a physical explanation for the mechanism behind it. It tells us the outcome without telling us what time actually is. To find that mechanism, we have to stop looking at time as an invisible container that everything moves through. Instead, mode identity theory offers a purely mechanical alternative. Think about how we actually track time. Every clock we've ever built, from swinging pendulums to vibrating cesium atoms, does exactly the same thing. They don't measure a flowing river. They count cycles of something periodic. Classical physics treats time as the background container, tracking how long those cycles take. Mode identity theory proposes the opposite. Time is the measurement of phase advance on a fundamental wave. In this framework, the universe exists as a standing wave mapped onto a closed three-sphere. Embedded inside is a Möbius surface. Its boundary forms a one-dimensional circle, the edge where the wave becomes an observable signal. Time is phase advancing along that boundary. Each step forward is a tick. The geometry mandates exactly 120 symmetrical steps to complete the cycle. Each step, an interval of precisely pi/30 radians, is 1 chronon, the absolute minimum sample rate. This means time is not continuous. Reality is geometrically pixelated. There is no physical space between these chronological ticks for anything to happen. This geometric structure explains exactly what's happening to our GPS satellite, replacing the curved space-time of relativity with the mechanics of a standing wave. This diagram illustrates a universal standing wave, behaving much like a plucked guitar string. It inherently has loud spots with high amplitude movement and quiet nodes at the ends that don't move at all. Gravity shifts your position. Earth pulls us to a quieter spot, but the satellite sits at a louder spot. Higher amplitude generates those 38 extra microseconds. Near a black hole, you slide to a zero amplitude node. Tick rate drops to 0, and observation stops. Velocity affects this mechanism too. High-speed particles called muons regularly reach the ground from the upper atmosphere because their internal clocks run slow. When an object moves at high speeds, its temporal edge, the circular boundary it samples along, physically contracts in our frame of reference. Because the circle is thinner, fewer of those discrete chronon steps fit into our observational window. Both frameworks yield the exact same highly precise mathematical predictions, but one requires time to stretch like abstract rubber, while the other derives the delay from tangible mechanical wave dynamics. The hardest part of this to grasp is that time does not flow like a river, it ticks. The standard model of cosmology assumes the cosmos is a sprawling container, with a master clock ticking away in the background to govern events. Instead, mode identity theory strips away the container entirely. The physical underlying geometry of the universe is the clock itself. Every second passing on the device you are watching this on right now is simply a measurement of the universe snapping forward by an indivisible angle. Time isn't what's passing. Time is where you are.